Hey guys, Dr. Tim Kruse, Elementary Statistics. We're going to do more hypothesis testing. This is difference of means. So that's the difference of averages. We're going to see, is there really any significant difference between one population and another? So for example, I'm in Oklahoma. Maybe I measure something about the people in Tulsa and I compare it to the people in Oklahoma City, all right? And I wonder, is there any big difference? I'm going to see how different they are and see if the difference is big enough to matter, if it's significant or not. If there's no big difference, then nobody cares. But if there's a big difference, well, now somebody cares. To use the z-table and get a z-score for our test statistic and our critical region traditional method rejection region, we're going to need to know both of the population standard deviations. So we're going to need to know both of sigmas to use the z-table. I'm going to use a 5-step process. It's pretty simple, but if you want a more detailed, in-depth explanation of what I'm using, see my first video. It was hypothesis testing, same thing, traditional method, sigma known. And if you'll go back to that video, it'll be a really detailed explanation of the 5 steps that I'm using. But probably just by watching this video you'll catch on. All right, so let's start with looking at this problem here. Education influences attitude and lifestyle. Differences in education are differences in education. There's differences. Differences in two populations' education level. Differences in education are a big factor in the generation gap. Is the younger generation really better educated? So they're going to compare younger people to older people. That's going to be our two populations. We're going to see if they're different. Of course they will be, all right? Nobody's exactly the same, but we're going to see if they're different enough to matter, if they're significantly different. So large surveys of people age 65 and older, we'll just call those the old folks like me, were taken from 40 cities. That's number 1, all right? That's the number of samples in group 1. The sample mean, that's going to be X bar, all right? It said sample, right? Sample is X bar. The sample average for these cities showed that X bar is 15.2%. We're just going to write 15.2. 15.2% of older people had attended college. Large surveys of young adults, this is going to be group 2, population 2, were taken from 39 cities. So group 2 had 39 samples. The sample mean, the sample average, that's X bar for group 2, is 17.7%. Let's just pause right there. So you took a sample in one of older adults and got 15.2% went to college, and you took a sample of younger adults and 17.7% went to college. Now it appears that young people go to college more often than older people did. So it does appear that there's a difference there from 15.2 to 17.7. All right, there is a difference. We need to test this and see if it's a significant difference, if young people go to college significantly more than older people did. All right, of course, it's never ever going to be exactly the same, so it's always going to be different. The question is really, is it different enough to matter? Is it significantly different? So it showed 17.7% of young adults had attended college. From previous studies, it is known that, and they gave us both of the population standard deviations. So group 1 is, well, we don't know what mu is, but the standard deviation is give or take 6.6, and the standard deviation for group 2 is give or take 4.4. Does this information, I can't read, does this information indicate that the population mean, the population average, of young adults who attended college is higher than that of older adults, and uses a level of significance of 0.05. So we got a 5% level of significance. All right, now I underlined this. Young adults is higher because they're trying to trick you with the words. You'll see here in a second when we organize our information. You got to be careful and read so you know what kind of test you're running. If it's a less than test, which is left-tailed, or a greater than test, which is right-tailed, or a different from, which this is not, because they said it's higher. So I just got to figure out which way the less than or greater than symbol is pointing. All right, let's organize our information here. So before we even get started with the 5-step process, we're going to organize our information. So the first group that they mentioned, group 1 from 40 cities, that was the older folks. And I like to label my column, my group 1 column, with a word that helps me make sense of how I'm going to phrase my challenge for my hypothesis. All right, so the older folks, there were 40 of them. They didn't give us the population average. All right, it's unknown, but that's okay. I'll show you why in a second. They gave us the population standard deviation. Now, when they give us both of the population standard deviations, both of the sigmas, that means we're going to use the Z table for our test statistic. You took a sample on group 1, the older folks, and you found that 15.2% of them went to college. And we don't know the sample standard deviation, but that's okay. If they give you the population standard deviation, we're going to use the Z table, and we don't really need the sample standard deviation. So here's your population numbers, here's your sample numbers for group 1. And then group 2 was labeled as the young adults. So young adults, and they labeled it N2. So there were 39 young adults sampled. Again, we don't know the population average, but we know the population standard deviation that was given. You took a sample and came up with 17.7% of the younger ones went to college. And again, we don't know sample standard deviation, but that's okay. We don't need it if we know sigma. All right, now notice I put a symbol here between the words. I kind of like to phrase my hypothesis in English first, and then we'll go through the 5-step process and do it, all statistically. So let's look at the question again. It says, does the information indicate that the average young adult is higher? They want young to be higher than older. All right, if you guys learned that this is an alligator and it eats the bigger number, they're saying young is higher than older. Young is going to be my bigger number. So I need this inequality symbol opening up toward the young. All right. You're tempted to write, if you just read this real fast and you're not careful and you see the word is higher, you think that's automatically a greater than symbol. So you're tempted to say older is greater than young. All right. You're tempted if you read it too fast. You got to be careful and read all the words. All right. Now, which group is higher? Because that's where this needs to open up toward. Does it open up toward the older or does it open up toward the younger? So the young adults is higher. That means the inequality needs to open up toward the young adults. All right, then I just make a note over here. Alpha is 5%. So that's our level of significance. We're going to shade 5% of the curve as a rejection region. Now, since it's a less than, this is going to be a left-tailed test. That means I'm going to shade this much of the curve on the left. I'm going to shade the left tail. And we'll draw a picture here in just a second. All right, so let's label the hypothesis. Now, we're trying to see if there's a difference between the populations. The null hypothesis always says there's no difference. They're saying population 1 went to college exactly as much as population 2. They're saying the older folks went to college just as much as the younger folks. They're saying there's no difference. So the null hypothesis, H sub 0, the null hypothesis says no difference, and it's always going to have an equal sign. It's just saying both the populations are the same. Your challenge comes from, like the last sentence in this paragraph. We have to phrase this challenge. Okay, I want to say this group is less than this group. I'm going to say group 1 is less than group 2. I'm arguing with the null hypothesis. The null hypothesis says the two groups are the same. The two group averages are the same. My challenge is no. The older group went to college less than the younger group. That's my challenge. All right. Step 2, I usually draw a picture and I color my rejection region. Now this is a left-tailed, less than is left-tailed. That means I'm going to shade 5% of the curve. So I got to figure out, if this is 100%, I need to put 5% shaded and 95% not. All right, 5% shaded and 95% not. I got to figure out what Z number I'm talking about here because I got to know where to draw this line. So I'm looking for the Z number that has 5% of the curve to the left. Whoops, and there's several ways of doing it. So quickest, easiest way, you guys that like to use your calculator, is just go to, let me clear that, go to second distribution, and you want a backwards normal distribution. Inverse means backwards. You're going to tell them the area, and they're going to work backwards and tell you what the Z number is that produced that area. So it says, hey, what's your area? 5%. What's mu? Well, on a standard normal curve, mu is 0. That's the middle. and you go by ones. So that's always going to be 0 and 1. And then paste it into your regular calculation window, hit enter one more time, and it says negative 1.645 is where I should start shading there. All right. You can always use your table. Let me grab the table here. All right, so you can always use your table. If we look at our table here, these are all the areas to the left of the certain z numbers. So I'm looking for 5% to the left. Oops, I was actually on the wrong page of my z table. I want to be on the negative side because I'm over here on the left side, the left tail. So these are all negative z numbers. I need to be on the negative z number page. Okay, back to what I was looking for. I'm looking for 5% area to the left. 5% area to the left. Now I'm looking through here, and right there, this is 5% and a little bit extra, and this is a little bit below 5%. It's actually exactly halfway between these two, which is negative 1.6. And then if we scroll up, exactly halfway between will be 4.5. All right, so negative 1.645. And of course, if you have this handy dandy cheat sheet, well, that's on the other page, flipping back and forth. If you have this dandy little cheat sheet at the bottom, we are looking for a alpha level of 5%. So I want to shade 5% of the curve. Now, what kind of test is it? It's a left-tailed test. And they said for 5% left-tailed, you start shading from negative 1.645 to the left. So however you find it, figure out where to draw the line. Find the z number that has this area, this alpha level of significance. If it says 5%, you're going to want a number z negative 1.645. Now, if we just, by the way, if this was pointing the other way, if it was greater than, I'd want 5% over here, which would be the positive twin of that number. It'd be 1.645 to the right, would leave 5% on the right. All right, next we got to run our test. Based on our samples, based on the 15.2% older people minus the 17.7% younger people, using my sample data information, I'm going to run this test, and I'm going to take my numbers and change them into a 0, 1, 2, 3 z number. All right, this is a conversion formula. It's just the difference between the populations. Difference means minus. And then you're dividing it by standard deviation. This is just a really messed up adjustment for standard deviation. It tells you how many steps left or right to go. So here's our difference divided by standard deviation. Tells me I need to take 1.99 steps to the left. So that's almost 2 steps to the left. Here's 0 in the middle. This is negative 1. There's negative 2. And just inside of negative 2 is where my test data landed. I converted my test data to a 0, 1, 2, 3 number. I placed it on the curve I placed it on the axis as a dot. And now I make a decision. If it lands in the shaded area, I get to reject what they said. They said there's no difference. They said the populations are exactly equal. I ran a test with my data. I ran a test and I landed in the rejection area. That means I get to reject what they said. That means my challenge was correct. If it would have landed anywhere here in the white area, 5% here, 95% here, if it would have landed anywhere in the white area, I would have to accept what they said. But it didn't. It landed in the rejection area. This is the traditional method. If it lands in the critical region, this is called critical region. That's a critical value where the region starts. And my test statistic landed in the rejection region, the critical region. If it lands in the critical region, I get to reject what they said. So I'm going to reject what they claim. HO is the advertised claim, the accepted average, the population mean, the population average, has lots of names. But I'm going to reject what they claim. Their claim was there's no difference. And my claim was, yeah, there's a significant difference. So here's how I phrase it every time. I say there is enough evidence, because I wanted to prove them wrong. So I had to gather a bunch of evidence. I got enough evidence at the 5% level of significance to conclude that. And then after the word that, I just kind of rephrase my challenge from the paragraph above from the story to conclude that the population mean percentage of young adults who attended college is, and I like to throw in significantly, is significantly higher. All right, I'm just copying that, the population mean percentage of young adults who attended college is higher. I just threw in the word significantly, all right? Because yeah, it's higher, but if it's just a little bit higher, nobody cares. It has to be significantly higher. All right, a random sample of N sub 1. This is group 1. There were 16 in that group. 16 winter days in Denver. All right, I'm going to name group 1 Denver. And there's 16 days were sampled. Gave a sample mean, that's X bar. That's mean means average. That's the average of your sample. That's X bar. X bar group 1 is 43. Okay. Previous studies show that population standard deviation, or sigma, for group 1 was 11. So sigma for group 1 is 11. If they give you sigma, specifically both sigmas, you get to use the z-table. All right. For Englewood, that's going to be group 2. So I labeled group 2 Englewood. A random sample, that's X bar, of the number in group 2 is 10. So there were 10 sampled in Englewood. And X bar was 49. So the average of my sample, group 2, the average of my group 2 sample was 49. Previous studies show that the population standard deviation for group 2 would be 10. So sigma group 2 is 10. Assume the pollution index is normally distributed, great. In both Englewood and Denver, great. Do these data indicate, all right, here comes your challenge, that the mean population pollution index of Englewood, that's group 2, is different either way from that of Denver, that's group 1. So they just want to know if Englewood is different from Denver. So that's just a not equal sign. So we don't have to be as careful. You know, if it's a less than or greater than symbol, we got to make sure it's opening toward the right group. But if they just say different from, that's just going to be not equal. So it's not as important. You don't have to be as careful. Use a 1% level of significance. All right. Our sigmas are unknown. I'll show you why in a second. It really doesn't matter because the null hypothesis is saying they're the same. So essentially they're the same number. And when we calculate the test statistic, these mu's kind of go away. You'll see in just a second. All right. So let's set up our hypothesis. Our null hypothesis is the two populations are the same. The pollution index in Denver is the same as the pollution index in Englewood, or at least very, very small difference, all right? Of course, they're going to be a little bit different, but is it different enough that anybody cares? So it looks like the pollution index in Denver was 43 from your sample of 16 people, and the pollution index in Englewood was 49 from your sample of 10 measurements, not people, 16 measurements, 10 measurements. So it looks like from your sample that Denver is lower than Englewood. That could have been our challenge. We could have said Denver is lower than Englewood. We could have challenged that and tested it. But they chose to phrase the challenge as it's just different from. All right. All right. So if my alpha level is 1%, all right, if my alpha level is 1% on my challenge, that group 1 is different from group 2, significantly different. If my alpha level is 1%, I need to shade 1% of the curve. If it's a two-tailed test, so does not equal means a two-tailed test, it means I need 1% of the curve shaded, but I need to split this exactly in half. Now that's 1%. So if I split it in half, that means I'm going to put a 0.5% on the left tail and a 0.5% on the right tail. That's what this A divided by 2 means. I'm telling you how to find out how much is shaded here. It's 1% total, which means a 0.5% on the left and a 0.5% on the right. Now a 0.5%, you can do it on your calculator, just do 0.01 divided by 2. A 0.5% is a decimal is 0.005. That's what we're going to look for in the table if you want to do it the long way. So I need 0.5% here and 0.5% here. This is, again, this is called the critical region. It's where we reject what they claim. It's where we reject their advertised claim. So if we land in here on the right tail or on the left tail, we get to reject what they said. But if it lands anywhere here in the white, because there's 99% here in the white, 0.5% here, 0.5% here, and 99% in the middle adds up to 100%. If it lands anywhere here in the white, I have to accept what they said. I have to accept that the populations are virtually the same. There's no significant difference, which this is the easy way to say it, but the hard way to say it is, I tried to reject what you said and I failed. I tried to reject this. I tried to say, no, this is wrong, and I failed. It's kind of the hard way of saying accept. So if it lands in the shaded area, you reject what they said, null hypothesis. And if it lands in the white area, you accept what they said. You accept their null hypothesis. All right, we have to figure out where to start shading these, and there's an easy way and a hard way. All right, the hard way is look up this area, 0.005, look up that area in the z table and see what z number produced it. If you find this negative z number, then you know what the positive z number is as well, because the white area is exactly in the middle, so it'll be the same area on the left and right. It'll be the same z number on the left and right, except this one will be negative and this one will be positive. You guys on your calculators, you want to put in this area right here, and it will tell you the z number that gave you that area. So you're going to do inverse normal. You're going to put in 0.005, and it will calculate what that z number needs to be. But the quickest way, if you have your little cheat sheet here, quickest way is you want a 1% for a two-tailed test, and that's going to be 2.58 steps either way. It's going to be both the positive 2.58 and the negative 2.58. All right, which is where we get the 258s here. So find out where 258 is. That's one step to the right, 2 steps to the right, and a little more than half a step to the right. That's where you draw the line at 2.58 steps to the right. Shade it. That's 0.5% area. And then 0, that's 1 step to the left, 2 steps to the left, that's 2.5 steps to the left, shade it. So draw the line 2.5 steps to the left, shade it, and that's 0.5%. Now we run our test and we see where our dot lands. And you guys can already see it there, but just pretend you don't. Let's run the test. Here's our equation. Here's our full-blown equation. And this is why the mu's don't matter. You'll see in a second. All right, my full-blown test statistic equation is subtract your sample averages. So my sample average of 43 minus my sample average of 49 minus the difference between the population averages. Well, they didn't tell us that, but it doesn't really matter, because if they say that the two population averages are the same, when you subtract two numbers that are the same, that's going to be a 0. That's why most of the time we leave this part out, because it's always minus 0. It's kind of a overproduction. We're just kind of overdoing the formula. Most of the time we just say x1 minus x bar 1 minus x bar 2, and we leave this part off, this minus 0 part off. And the rest of it looks familiar from the last problem. Calculate that, you get negative 1.43 for your test statistic. So place that as a dot on your axis here, and that's 1 and about 4/10 of a step to the left. So here's 0, here's 1 step to the left, here's half a step to the left, that's 5/10, so 4/10 would be a little short of halfway. So my test landed right here. That means I failed, all right? I have to accept what they said. They said, hey, there's virtually no difference between those two pollution levels in those two cities. I said, wait, I think there's a significant difference, because look at my samples. My samples are 6 units apart. I think that's a significant difference. Well, we ran our test, and turns out, yeah, it's different, but it's not significantly different. So I have to cave. I have to accept what they said, but I'm going to say it the fancy way and say I failed to reject HO. I was trying to reject what you guys claimed, and I failed. So we failed to reject HO. And then this is your conclusion. Interpreting your conclusion, I just use the same words every time. There will be an is or an is not right here. All right. So I was trying to reject what they said, and I failed. That means I didn't gather enough evidence. My evidence was no good. So I did not have enough evidence. There is not enough evidence at the 1% level of significance to conclude that, and then just restate your challenge from the words, the mean population pollution index of Inglewood is, I like to throw in significantly different from that of Denver in the winter. That was my challenge. I tried to prove that they were significantly different, but I could not gather enough evidence. All right, so I failed. I failed to reject what they said. All right, so let's do one more and just call it good for the day. REM, rapid eye movement. Sleep is sleep during which the most dreams occur. Each night a person has both REM and non-REM sleep. However, it's thought that children have more REM sleep than adults, so they think that children dream more. Assume that REM sleep time is normally distributed. Good. That means we can use the z-table for both children and adults. A random sample in group 1 of 11 children showed that they have an average REM sleep time of 2.9 hours per night. All right, so they were dreaming 2.9 hours in group 1. From previous studies, it's known that the population standard deviation for group 1 is 0.8. Another random sample, all right, that's adults, so I've labeled it. Group 1 is children, group 2 is adults. Another random sample, whose number is 11, so 11 adults were sampled, showed they had an average dream time or REM sleep time of X bar group 2, 2.2 hours per night. Previous studies show that their population standard deviation is 0.5. Do these data indicate on average that children tend to have more REM sleep than adults? All right, you got to be careful here. All right, have more. You're tempted to say greater than, but it might be less than. It depends which order they put this in. You know, if they put adults here and children there, you got to be careful and make sure that it opens up toward the correct quantity. All right, now they said children have more than adults. Here's children, here's adults. I want this to open up toward the children. Children have more than adults. Children are greater than adults. That's going to be my challenge here in just a second. All right, so both groups of 11, mu is unknown, but we don't care because it just turns into 0 in our test statistic. Standard deviations, 0.8 versus 0.5. If they give you both of the sigmas, we get to use the z-table. All right, my sample in group 1 was 2.9. My sample in group 2 was 2.2. Now it looks like children sleep a little bit longer than adults. 2.9 hours versus 2.2 hours. So this looks like a good challenge. All right, based on my sample, based on my measurements, it looks like children sleep more than adults. All right, so that's a good sample. That's a good challenge. Sample standard deviation is unknown, but we don't need it if they give us the population standard deviation. All right, so the null hypothesis is always the two groups are the same. There is no difference between children's sleep time and adult sleep time, or dream time, or REM sleep time, however you want to call it. So they're saying they're equal. These are the exact same number, or really, really, really close. My challenge, the alternate hypothesis, is no, this is not right. My challenge is that children dream a lot more than adults, that children REM sleep time is greater than adult REM sleep time. So that's my challenge, all right? It's obvious from my sample, it's obvious that children have a higher number of hours than adults do, but is it significantly higher? Is it large enough difference that anybody cares? All right, here's our curve. I want to sketch 1% to the right. This is greater than. My challenge is greater than. It's a right-tailed test. So you want this to be 1%, and I left off the alpha equals 1% here. All right, I just like to say that 1% is shaded here, which means 99% is shaded over here, is not shaded, excuse me. So 99% from here to here, and 1% from here to here, all right? We got to figure out what z number produces an area of 1%. Now, if you want to look it up the hard way, in the table, the areas are only to the left. So if you're going to look up this z number in the table, you have to look up an area of 99%. So you're looking up an area of 0.9900, and your table will tell you what z number it is. Or you can do it the easy way and just use your little cheat sheet here. If you want to shade 1% of the curve to the right, you're going to start shading at 2.33. All right, you guys that like to use your calculator, you're going to do a second distribution. You want to do backwards normal, inverse normal. You want to tell it the area. I want an area of 1%. Mu is always 1, standard deviation is always 1. Paste it into your window and hit enter one more time. And there's your negative 2.33 as well.